Germans were surprised when proximity fuses wiped out entire formations. At the Battle of the Bulge, Colonel George Axelson stood in the pre-dawn darkness of December 16, 1944, facing a decision that would violate direct orders from the highest levels of Allied command. The commander of the 406th Artillery Group had just received desperate calls for help from the 38th Cavalry Squadron, dug in around Monschau, Germany. German forces were pouring through the Ardennes forest in what would become the largest battle ever fought by the United States Army. The lightly armed cavalry troopers were being overrun, and they needed artillery support immediately. Axelson had the weapon to save them. Sitting in his ammunition stores were crates of artillery shells marked with a cryptic code. Posseed. These shells contained a technology so secret that it was guarded at the same level as the atomic bomb. The Pentagon had explicitly forbidden their use over enemy-held territory for fear that a dud shell might fall into German hands, allowing the enemy to reverse engineer one of America's most closely guarded military secrets. Supreme Commander Dwight Eisenhower had been fighting for permission to use these shells for months, but authorization had not yet come through official channels. The sounds of battle grew louder. German infantry and armor were pushing forward under cover of the morning fog. American cavalry troopers were fighting and dying. Axelson made his decision. The emergency trumped the restrictions. He ordered his gunners to load the posset shells and open fire. Minutes later, the German attack formations advancing toward Monschau experienced something they had never encountered before in years of warfare across Europe and Russia. Artillery shells began exploding not when they hit the ground, not at predetermined altitudes set by timers, but at precisely 30 feet above their heads. The airbursts were perfect, consistent, and utterly devastating. Shrapnel rained down on troops who thought they were safe in their foxholes and trenches. The German assault collapsed in confusion and carnage. The soldiers who survived staggered back toward their lines in what witnesses would later describe as a dazed state. They had no idea what had just happened to them. The shells had given no warning, no chance to take cover, no time to react. Traditional artillery you could hear coming. You could dive into a hole, press yourself against the earth, and have a chance. This was different. This was death falling from the sky with scientific precision. Within hours, reports were flooding back to German command posts across the Ardennes. Something new was happening. American artillery had suddenly become far more lethal. Commanders who had fought on the Eastern Front against massed Soviet artillery, who had survived the bombardments of North Africa and Italy, who understood the calculus of casualties from conventional fire, were seeing casualty rates that made no sense. Entire formations were being decimated by what should have been survivable barrages. The Germans had just encountered the proximity fuse, a technology that would help turn the tide of the Battle of the Bulge and change the nature of artillery warfare forever. But the story of how this device came to be firing over the frozen fields of Belgium in December 1944 began years earlier in laboratories scattered across America, where scientists raced against time to solve a problem that many considered impossible, the problem that artillery could not solve. In the years leading up to World War II, military planners faced a fundamental problem that had plagued warfare since the invention of gunpowder. How do you make an explosive shell detonate at exactly the right moment and in exactly the right place to destroy a fast-moving target? For centuries, artillery had relied on two basic types of fuses. The contact fuse was the simplest. A shell with a contact fuse exploded only when it physically struck something solid. This worked well against buildings, ships, and ground targets, but it was almost useless against aircraft. A pilot only had to avoid being directly hit by the shell itself, which, given the speeds and altitudes of modern aircraft, was statistically unlikely in the extreme. The alternative was the timed fuse. An artillery officer would estimate how long it would take a shell to reach a certain altitude, set a mechanical timer on the fuse accordingly, and hope that an enemy aircraft would be nearby when the timer ran out and the shell exploded. This required complex calculations, accounting for the shell's trajectory, the wind, the temperature, the humidity, and the estimated position of a target that was moving at several hundred miles per hour. Even the best calculations were essentially educated guesses. During World War I, studies showed that it took an average of several thousand anti-aircraft shells to down a single airplane using timed fuses. By 1940, as Europe descended into war and Japan pushed deeper into Asia, the problem had become critical. Aircraft had evolved dramatically since the First World War. They were faster, more maneuverable, and carried larger bombs. The vulnerability of surface ships to air attack had been demonstrated repeatedly. The British Royal Navy lost the aircraft carrier. Courageous to a German U-boat in September 1939, but the real wake-up call came with the devastating effectiveness of German dive bombers and torpedo planes against surface vessels. The United States Navy understood that America's entry into the war was likely just a matter of time. And when it came, the Navy's ships would be operating in both the Atlantic and Pacific, facing determined enemy air forces. The existing anti-aircraft defenses were inadequate. Gunners were essentially throwing up a wall of exploding metal and hoping that something would hit. The waste was staggering, the effectiveness was minimal, and the danger to friendly forces and civilians was real. This danger became tragically apparent at Pearl Harbor. On December 7, 1941, when Japanese aircraft struck the American Pacific Fleet, anti-aircraft gunners aboard the ships and at shore batteries opened fire with everything they had. They fired thousands of shells into the sky, using timed fuses set to explode at various altitudes. Many of those shells, either because the timers were set incorrectly or because they malfunctioned, did not explode in the air at all. They came back down and detonated when they hit the ground in Honolulu. 48 civilians were killed that day, not by Japanese bombs, but by American anti-aircraft shells that had failed to explode properly over the harbor. It was a grim reminder that the technology of the time was not just ineffective against the enemy, it was dangerous to the people it was supposed to protect. Military researchers had been thinking about proximity detection for years. The concept was beautifully simple. Instead of guessing when and where to explode, why not give the shell some way to detect when it was near a target and trigger the explosion automatically? Various approaches had been considered. Optical systems that used a beam of light, sometimes infrared, and triggered when the reflection reached a certain threshold. acoustic systems that listened for the sound of an aircraft engine, capacitive or inductive methods similar to a metal detector that could sense the presence of a large metal object nearby. All of these approaches suffered from the same fundamental problems. First, the electronics of the late 1930s were large, fragile, and complex. Radio receivers and transmitters filled entire rooms. Vacuum tubes, the essential components of any electronic circuit before the invention of the transistor, were delicate glass devices that could barely survive being shipped across the country, much less being fired out of a gun. Second, an artillery shell had to be small enough to fit inside a gun barrel, cheap enough to be manufactured by the millions, and rugged enough to survive being handled by sailors and soldiers under combat conditions. The forces involved in firing an artillery shell were almost unimaginable. A 5-inch naval gun accelerated a shell from 0 to roughly 2,800 feet per second in a fraction of a second, creating an acceleration force of 20,000 times the force of gravity. At the same time, the rifling grooves inside the gun barrel grabbed the shell and spun it at up to 30,000 revolutions per minute to stabilize its flight. Imagine taking a delicate glass radio tube about the size and fragility of a small light bulb and subjecting it to forces equivalent to having a 140-pound person standing on it with all their weight concentrated on a stiletto heel. Then spin it so fast that the centrifugal forces would tear apart most materials. Then expect it to work perfectly as a miniature radio station, transmitting and receiving signals while hurtling through the air at nearly 3 times the speed of sound. This was the challenge facing anyone who wanted to build a proximity fuse. By 1940, as German bombs fell on London and the Japanese military machine swept across Asia, most engineers believed it could not be done. The technology simply did not exist, but most engineers had not met Merle Tuve. A physicist goes to war. Merle. Antony Tuve was born in 1901 in Canton, South Dakota, the son of Norwegian immigrants. He grew up in a household that valued education and hard work, showed exceptional aptitude in mathematics and physics, and earned his doctorate at Johns Hopkins University under the guidance of some of the most brilliant minds in American science. By 1940, Tuve was the head of the Department of Terrestrial Magnetism at the Carnegie Institution of Washington, conducting fundamental research into the nature of the Earth's magnetic field and the upper atmosphere. Tuve was known among his colleagues as brilliant, driven, and temperamental. He had little patience for bureaucracy, no tolerance for excuses, and an ability to cut through complex problems to identify the essential challenges. When war broke out in Europe, he understood immediately that American scientists would need to contribute to the defense effort. What he did not know was that he was about to lead one of the most important weapons development programs of the entire war. In June 1940, President Franklin Roosevelt created the National Defense Research Committee, or NDRC, under the leadership of Vannevar Bush. Bush was a former MIT professor, an engineer and inventor, and a master of scientific organization. He understood that modern warfare would be won or lost based on technological superiority, and he was determined to harness the full scientific capacity of the United States for the war effort. Bush divided the NDRC into sections, each focused on a particular area of weapons research. Section T, created in August 1940, was dedicated to the development of proximity fuses. The designation, Section T, was deliberately vague. The work was classified at the highest level. Bush placed Merle Tuve in charge, and Tuve assembled a small team of physicists and engineers at the Carnegie Institution's Department of Terrestrial Magnetism in Northwest Washington. The team included Richard Roberts, a physicist who had worked with Tuve on nuclear research, Lawrence Hofstad, Lloyd Berkner, and several other brilliant scientists who set aside their peacetime research to tackle what many considered an impossible problem. The breakthrough came from an unexpected source. In September 1940, a British scientific mission led by Sir Henry Tizard arrived in the United States, carrying some of the most closely guarded military secrets of the war. The Tizard mission, as it came to be known, was a desperate gamble by a Britain that was fighting alone against Nazi Germany. The British brought with them plans and prototypes for cavity magnetrons, which made modern radar possible, designs for jet engines, details of early computer systems, and, crucially for Section T, a circuit designed for a proximity fuse based on a radio oscillator. The British had been working on proximity fuses since before the war, but they had focused on what they called unrotated projectiles, rockets, and bombs that did not have to survive the extreme accelerations and spin rates of artillery shells. Their circuit design was ingenious. It used a single vacuum tube as both a radio transmitter and a receiver, a setup that would emit a continuous radio frequency signal and detect the reflections coming back from nearby objects. When the reflected signal reached a certain strength, indicating that the shell was very close to a target, the circuit would trigger an explosion. Tuve and his team looked at the British design and immediately grasped both its potential and the immense challenges involved in making it work in an artillery shell. The concept was sound, but everything would have to be miniaturized, ruggedized, and simplified. They would need vacuum tubes that could survive forces no vacuum tube had ever been designed to withstand. They would need batteries that could be stored for months and then deliver power instantly when needed. They would need circuits that were simple enough to be manufactured by the millions and reliable enough to work under combat conditions. Tuve attacked the problem with characteristic intensity. He assembled a team that eventually grew to more than 1,000 scientists, engineers, and support staff. He established a working environment that prioritized speed over perfection, results over elegance. On the walls of the laboratory, he posted a series of directives that captured his philosophy. I don't want any damn fool in this laboratory to save money. I only want him to save time. Shoot at an 80% job. We can't afford perfection. Don't try for an A in award D is necessary and enough, but an F is fatal. The first major challenge was the vacuum tubes. In early 1941, Section T began experimenting with miniature tubes designed for hearing aids. These tubes were much smaller than standard radio tubes, about the size of a thimble, but they were still far too fragile. The team began dropping tubes from various heights onto concrete and armor plate to test their durability. To everyone's surprise, some of the tubes survived. It was not much, but it suggested that with the right design modifications, rugged enough tubes might be possible. This was where James Van Allen entered the story. Van Allen, who would later become famous as the discoverer of the radiation belts surrounding Earth, joined the Applied Physics Laboratory at Johns Hopkins University in 1942. He brought with him expertise in building instruments that could survive being launched on high-altitude rockets, and he understood the principles of designing electronic components to withstand extreme forces. Working with manufacturers like Western Electric and Raytheon, Van Allen and his colleagues redesigned the miniature vacuum tubes from the ground up. The key innovations came from understanding exactly what failed and why. When a vacuum tube was subjected to 20,000 G of acceleration, every component inside tried to tear itself apart. The filaments that heated up to emit electrons would snap. The grid structures that controlled electron flow would collapse. The glass envelope itself would shatter. Van Allen's team reinforced the filaments with thicker wire, redesigned the internal structures to distribute the forces more evenly, and developed new manufacturing techniques that created stronger glass envelopes. They tested each modification by mounting tubes in centrifuges and spinning them at forces equivalent to being fired from a gun. They dropped them from the third floor of the Pratt Library in Baltimore. They fired them in test guns and examined what broke and what survived. By mid-1941, they had tubes that could survive the acceleration. The next challenge was the battery. Traditional dry cell batteries were too large and had limited shelf life. The team developed a wet cell battery that used a clever activation mechanism. The battery consisted of a small glass tube filled with an electrolyte solution. When the shell was fired, the centrifugal force from the spin pushed the liquid outward until it contacted metal electrodes arranged around the tube. The chemical reaction between the electrolyte and the electrodes produced electrical current that powered the fuse. The beauty of this design was that the battery remained inert until the moment it was needed, giving the shells an indefinite shelf life. The circuit design went through countless iterations. Lloyd Berkner developed a key improvement that used separate transmitter and receiver circuits, making the system more reliable. The final design used a simple but elegant approach. One vacuum tube served as a radio oscillator, generating a continuous signal at radio frequencies. The projectile's body served as the antenna, broadcasting this signal in all directions. When the signal reflected off a nearby target and returned to the fuse, it created an interference pattern with the outgoing signal. This interference produced an audio frequency beat that could be detected, amplified by additional vacuum tubes, and used to trigger a thyratron tube that acted like an electronic switch. When the signal reached the right strength, indicating the shell was within about 70 feet of a target, the thyratron would fire, sending a charge to an electric detonator that set off the main explosive. The system also included several safety features. Setback switches ensured that the battery circuits only closed when the shell was actually fired, preventing accidental detonation. An electrical arming delay prevented the fuse from activating until the vacuum tubes had warmed up and the shell had traveled a safe distance from the gun. For anti-aircraft use, the fuse needed a way to distinguish between an aircraft target and the surface of the ocean, since shells fired from ships often traveled over water. The wave suppression feature, or WSF, reduced the sensitivity of the circuit to steady reflections, like those from ocean waves, while remaining responsive to the rapidly changing reflections from a moving aircraft. By August 1942, after 2 years of intensive development, Section T was ready for a real test. The cruiser USS Cleveland steamed into Chesapeake Bay with its 5-inch guns loaded with proximity-fused shells. Radio-controlled drone aircraft were launched to serve as targets. The Navy officers observing the test expected to see some improvement over conventional fuses, but nothing prepared them for what actually happened. The Cleveland opened fire. The first shells detonated near the drones with perfect precision, sending them tumbling into the bay in pieces. The test was supposed to run for 2 days, but it ended on the first day because they ran out of drones. The proximity fuses had destroyed all 3 targets with just 4 shells. The Navy observers were stunned. They had never seen anything like it. Anti-aircraft fire that actually worked. From laboratory breakthrough to mass production, creating a proximity fuse that worked in a laboratory was one thing. Manufacturing millions of them under wartime conditions, maintaining absolute secrecy, and ensuring consistent quality was an entirely different challenge. The transition from prototype to production weapon would require one of the largest industrial mobilizations of the war, involving more than 100 factories, tens of thousands of workers, and $1 billion in 1940s money, equivalent to about $15 billion today. Tuve and his team understood from the beginning that the fuse would only matter if it could be produced in vast quantities. A single cruiser firing all its anti-aircraft guns in combat could go through hundreds of shells in minutes. The Pacific Fleet, when fully deployed, would need millions. The Applied Physics Laboratory, which had grown from Tuve's original Section T team, took on the role of designing the fuse for mass production while coordinating with industrial partners to solve the manufacturing challenges. The proximity fuse, when complete, contained about 130 miniaturized electronic parts packed into a space not much larger than a man's fist. Each component had to be manufactured to precise specifications, assembled by hand, and tested under conditions that simulated the extreme stresses of combat. The vacuum tubes alone presented an extraordinary manufacturing challenge. Each fuse required 5 miniature tubes, which meant that producing 1 million fuse required 5 million tubes. At peak production, American factories were turning out proximity fuse fast enough to require 2 million vacuum tubes every week. The primary manufacturer of these tubes was Sylvania Electric Products, but the company had to be essentially rebuilt to handle the task. The Sylvania plant in Ipswich, Massachusetts, became the single largest producer of proximity fuse components in the country, eventually manufacturing more than 5 million fuses. The work was done almost entirely by women. These were not trained engineers or experienced factory workers. They were housewives, young women fresh out of high school, anyone who could be trained to perform the delicate assembly work that the fuses required. The women worked in conditions of absolute secrecy. When they entered the factory, they were searched. When they left, they were searched again. They were forbidden from bringing purses into the building. They were not allowed to discuss their work with anyone, not even their husbands or families. Most of them had no idea what they were actually making. They knew only that it was important, that it was secret, and that the work required incredible precision. Each vacuum tube was smaller than a pencil eraser, made of glass so thin it could barely be handled, filled with wire filaments and metal grids that had to be positioned with tolerances measured in fractions of a millimeter. The women assembled these tubes by hand, one after another, hundreds per day. Mary Conley, Phyllis Hills, Victoria Sibis, Helen Thurber, and thousands of other women whose names have been largely forgotten by history performed this painstaking work for years. They learned to handle components so fragile that a slight pressure would destroy them. They worked under magnifying glasses, fitting pieces together with tweezers, soldering connections with precision that would have challenged a jeweler. The tubes were then tested by machines that subjected them to simulated firing forces, spinning them in centrifuges and dropping them to ensure they could survive the journey from gun to target. The human cost of this work only became apparent decades later. The solder used in the assembly process contained beryllium, a metal that can cause severe lung disease with long-term exposure. Many of the women who worked on the proximity fuse developed health problems years afterward. The latency period for beryllium exposure can be 60 years, meaning that women who assembled fuses in 1943 might not develop symptoms until the early 2000s. Some contracted malignant mesothelioma and other forms of lung disease. They had given their health in service to their country, working in secrecy on a weapon whose very existence they did not fully understand. The assembly of complete fuses took place at 5 main factories: Crossley Corporation in Cincinnati, Ohio, RCA, Eastman Kodak, McQuay Norris, and Sylvania. The Crossley Corporation became the second largest producer after Sylvania. Lewis Crossley, the company president, described the operation in a post-war interview as running around the clock, 7 days a week, with 10,000 employees working in shifts. At peak production, Crossley alone was producing 16,500 fuses per day. The company manufactured more than 5 million fuses during the war, about 24% of the total production. Quality control was obsessive. Every fuse had to pass multiple tests before it could be loaded into a shell. The vacuum tubes were tested in centrifuges that simulated the acceleration of firing. The complete fuses were subjected to rough handling, temperature extremes, humidity, and vibration. In one test, fuses were deliberately dropped on concrete to ensure they could survive being accidentally knocked off a table. In another test that became somewhat infamous, some fuses were tested by firing them at the ground in cold weather, only to have them fail repeatedly until someone realized the ground had frozen solid, creating test conditions that were unrealistically harsh. The security surrounding the program rivaled that of the Manhattan Project. The fuses were given the codename VT for variable time, a designation deliberately chosen to be misleading. If anyone asked what VT meant, the official answer was that it was a new type of timed fuse with a variable timer setting. This was technically true, but revealed nothing about the actual mechanism. The codename POSIT was used by the Army for their supplies of proximity-fused shells. Workers in the factories knew they were making something important for the war effort, but the details were kept strictly compartmented. Even within the military, only those with specific clearances were told how the fuses actually worked. The fear of the secret falling into enemy hands was so great that for most of the war, proximity fuses were only used over water or in situations where recovery by the enemy was impossible. The Navy began using them in combat in early 1943, but strict procedures were followed to minimize the risk. If a fuse failed to detonate and fell into the ocean, it was considered safe because the salt water would quickly corrode and destroy the electronic components. Ships were ordered to track where their shells fell and to avoid firing proximity-fused ammunition over land, where the enemy might recover intact examples. This restriction created enormous frustration among military commanders who understood the potential of the weapon. The fuses had proven their worth against Japanese aircraft in the Pacific. They had saved British cities from V-1 flying bombs. But the Army's artillery, fighting across Europe, was forbidden from using them for fear that a dud might fall behind German lines. General George Patton, never known for his patience with bureaucratic restrictions, repeatedly requested permission to use proximity fuses with his Third Army artillery. General Dwight Eisenhower, the supreme commander of Allied forces in Europe, argued strenuously that the tactical advantage outweighed the security risk. But the Pentagon remained unmoved. The secret was too valuable to risk. That calculus changed on December 16, 1944, when German tanks and infantry poured through the Ardennes forest in the largest German offensive of the war. December, in the Ardennes, Hitler's last gamble. By late 1944, Nazi Germany was losing the war on all fronts. In the East, Soviet armies had liberated most of Eastern Europe and were approaching the German border. In the West, American, British, and Canadian forces had broken out of Normandy, liberated France, and entered Germany itself. German cities were being reduced to rubble by round-the-clock bombing. The Wehrmacht, once the most powerful military force in the world, was being ground down by the sheer weight of Allied material superiority. Adolf Hitler, however, was not a man inclined to accept defeat. In the autumn of 1944, he conceived a desperate plan for a counter-offensive that would split the Allied armies, capture the vital port of Antwerp, and force the Western Allies to negotiate a separate peace. This would allow Germany to concentrate all its remaining strength against the Soviet Union. Most of Hitler's generals thought the plan was madness. Germany no longer had the resources for a major offensive. The armies were exhausted, fuel was critically short, and the Luftwaffe had been bled white by years of attrition. But Hitler insisted, and in Nazi Germany, Hitler's word was law. The Germans assembled their forces in complete secrecy, massing more than 200,000 troops and nearly 1,000 tanks in the heavily forested Ardennes region of eastern Belgium and northern Luxembourg. They chose this area precisely because the Americans considered it an unlikely place for an attack. The Ardennes was densely wooded with few good roads, and the terrain favored the defender. The American commanders had placed their most battered divisions there to rest and recuperate, and had stationed inexperienced replacement units in the area, considering it a quiet sector where green troops could gain experience without facing heavy combat. The Germans struck just before dawn on December 16, 1944. They had waited for a period of bad weather that would ground Allied aircraft, negating the Allies' overwhelming air superiority. In heavy fog and snow, German infantry infiltrated American positions, while panzer divisions smashed through weak points in the line. American units were overrun, surrounded, and forced to retreat in confusion. Within hours, the Germans had penetrated miles behind American lines, creating a bulge in the Allied front that would give the battle its name. The American response was initially chaotic. Communications were disrupted, command and control broke down, and no one at higher headquarters had a clear picture of what was happening. But as the first day progressed, American units began to fight back with a determination that surprised the Germans. At the town of St. Vith, American forces held out for days against overwhelming odds, buying crucial time for reinforcements to arrive. At Bastogne, the 151st Airborne Division was surrounded, but refused to surrender, tying down German forces that were desperately needed elsewhere. On the northern shoulder of the German advance, American units at Elsenborn Ridge held their ground and inflicted terrible casualties on attacking German formations. What the Germans did not know, what they could not have known, was that the American artillery was about to unleash a weapon that would turn their carefully planned offensive into a slaughter. Within 2 days of the German attack, the Pentagon lifted the restriction on using proximity fuses over enemy-held territory. The decision came from the highest levels. Eisenhower had been demanding this for months, and now, with American forces fighting for their lives in the snow and fog of the Ardennes, the security concerns were overridden by tactical necessity. Orders went out to artillery units across the front. You are authorized to use posit ammunition. 200,000 proximity-fused shells had already been shipped to Europe and distributed to ammunition dumps behind the American lines. Artillery officers who had been briefed on the fuses but forbidden to use them now received permission to load them and fire. The gunners themselves, most of whom had never seen these special shells before, were given quick briefings on what made them different. They were told only that these shells would explode in the air at a preset height, that they should be used against concentrations of enemy troops in the open, and that they were not to discuss them with anyone. The first documented use of proximity fuses against ground forces came at Monschau, where Colonel Axelson made his fateful decision to ignore the official authorization delay and fire immediately to save the 38th Cavalry Squadron. But within days, proximity-fused shells were being fired by artillery batteries all along the Ardennes front. The effects were immediate and devastating. The Germans had learned to cope with conventional artillery fire. When shells with timed fuses were incoming, soldiers dove into foxholes, shell holes, trenches, or any depression in the ground. The explosions would throw shrapnel and blast effects outward and upward, but a man pressed flat against the bottom of a hole had a reasonable chance of survival. The Germans had also learned that in bad weather, when clouds and fog prevented aerial observation, the accuracy of American artillery decreased significantly because forward observers could not see where the shells were landing. German commanders had factored this into their planning for the offensive. They believed that the winter weather would provide some protection from American artillery, allowing their troops to move more freely during the day. The proximity fuse changed everything. German soldiers advancing across open ground or regrouping in staging areas, suddenly found themselves under a type of artillery fire they had never experienced before. The shells made no sound as they approached. High-velocity artillery always arrived faster than the sound of its firing, but with proximity fuses, the shells never hit the ground to produce the distinctive explosion that might give soldiers a split-second warning to take cover. Instead, the shells detonated 30 to 50 feet in the air, directly above the troops below. The effect was catastrophic. Shrapnel from an airburst travels downward and outward in a cone-shaped pattern. Foxholes, trenches, and shell holes offered almost no protection. A man hiding in a hole was actually in more danger from an airburst than a man standing up, because the shrapnel was coming from directly overhead. Even substantial fortifications provided limited safety. The high-velocity fragments penetrated wooden logs and pierced through the roofs of bunkers that would have been safe from ground-level explosions. German prisoners of war, when questioned about the artillery, described it in terms that revealed their confusion and fear. They did not understand what was happening. They knew artillery had survived countless bombardments on the Eastern Front and in North Africa and Italy, understood how to take cover and when to move. But this was different. This was death from above, with no warning and no defense. Prisoners emerged from barrages in what American intelligence officers described as a dazed state, clearly traumatized by an experience that defied their expectations of how artillery worked. German commanders quickly realized they were facing a new weapon, but they had no idea what it was or how it worked. Initial reports spoke of shells that hung in the air and exploded with unnatural precision. Some officers speculated that the Americans had developed a new type of timed fuse calibrated with unprecedented accuracy. Others believed it was some form of radar-guided artillery. A few even suggested chemical weapons, so inexplicable were the casualty patterns. None of these explanations fit the evidence. Traditional countermeasures failed completely. Spreading out formations did not help. Digging deeper foxholes made things worse. Moving at night, long a German specialty, provided no protection. The shells did not care about darkness or fog. They did not rely on observers or visibility. They simply sensed the presence of men and exploded at the worst possible moment. At Elsenborn Ridge, where German infantry and armor repeatedly attempted to break through American lines, proximity-fused artillery turned every advance into a massacre. German units that emerged from the forest to form up for attacks were shredded before they could even begin moving. Officers trying to regroup their men were killed along with their radio operators. Assault waves dissolved before reaching American positions, leaving the ground littered with bodies and equipment. At Bastogne, where German forces encircled the town and attempted to crush the defenders, American artillery firing proximity-fused shells broke up attacks before they could close. Even when weather-grounded Allied aircraft, artillery with VT fuses filled the role of air power, dominating the battlefield with impunity. German soldiers later described feeling as if the sky itself had turned hostile. Captured German after-action reports from the Ardennes make grim reading. One regimental commander wrote that his unit had been rendered combat ineffective in less than an hour by artillery fire of a new and unknown type. Another noted that morale collapsed rapidly once troops realized that no form of cover was effective. Veterans of the Eastern Front, men who had survived Stalingrad and Kursk, admitted they had never experienced anything comparable. The proximity fuse did not win the Battle of the Bulge by itself. German fuel shortages, Allied reinforcements, clearing weather that restored air superiority, and Hitler's strategic miscalculations all played decisive roles. But the fuse acted as a force multiplier of extraordinary power. It magnified American artillery's effectiveness to such a degree that German units lost the ability to mass, maneuver, or recover from setbacks. By January 1945, the German offensive had collapsed. What began as Hitler's last gamble ended as a catastrophic defeat. Tens of thousands of German soldiers were dead or captured. The Wehrmacht had expended irreplaceable reserves of men, tanks, and equipment for nothing. The Western Allies resumed their advance toward the Rhine, and Germany's fate was sealed. Only after the war did the full story of the proximity fuse emerge. German scientists examining captured Allied ammunition were astonished when they finally understood what they had faced. A miniature radio transmitter and receiver inside an artillery shell. A device that turned explosives into intelligent weapons decades before the term existed. In retrospect, the proximity fuse stands as one of the most important technological breakthroughs of the Second World War. It dramatically increased the effectiveness of anti-aircraft fire, protected Allied ships from air attack, neutralized V-1 flying bombs, and, on the frozen battlefields of the Ardennes, shattered German ground forces at the moment of their last great offensive. It was not just a weapon. It was a demonstration of what happens when science, industry, and battlefield necessity converge. The Germans had prepared for tanks, for aircraft, for artillery, as they understood it. They had not prepared for a shell that could think. At the Battle of the Bulge, that difference proved fatal.